Okay, hello and welcome to part 3 in this video series where we're looking at the June 2013 mechanics paper. So on question 3 it says define the force constant of a spring. Okay, so this is just the force per unit area. Okay, that's what the force constant is. So if you remember the equation F equals minus kx for a spring, this k here, that's the spring constant. And you can see what the spring constant tells you if you just solve for k. So k equals F over x. So F is a force, x is the extension, so that's going to give you units of newtons per meter. Okay, what is that telling you? Well, that's telling you if you have, for every, because it's per meter, for every 1 meter extension, it tells you how big the restoring force is. So let's give an example. If the spring constant is, let's say it's 10 newtons per meter, that means for every 1 meter extension, there's a restoring force of 10 newtons. So it essentially is kind of a measure of the stiffness of a spring. Because if you have a force constant that's 100 newtons per meter, that means every time you extend that spring by 1 meter, there's a restoring force of 100 newtons. So that's a bigger restoring force. So it's like a stiffer spring. Okay, and you always know that the restoring force is opposite to the direction of the extension. That's why in F equals kx is a minus kx. Tells you that the restoring force is in the opposite direction, and that's because the spring wants to go back towards its original equilibrium position. Okay, so if we just move on to the next part, there's a trolley attached by 2 stretched springs, A and B, so they're already stretched, which means there's already an extension being applied to them. Okay, it then says the trolley is on a horizontal table and at rest. It says the springs are identical. And then it says on figure 3.1, draw an arrow to show the direction of the force exerted by spring A on the trolley. Okay, well we know that these springs have been stretched, so there will be a restoring force. Remember what I said about F equals minus kx. And the restoring force is always in the opposite direction to the extension. So if spring A is stretched, it's obviously going to be a restoring force back in this direction, because that's the direction it wants to go, because it wants to get back to its equilibrium position, so before it's stretched. So it's going to exert a force to the left. Okay, so the force from the spring onto the trolley is to the left. Okay, so the next part, the mass of the trolley is 0.8 kilograms. The force constant of each spring, remember they said they're identical springs, is 14 newtons per meter. A student pulls the trolley to the left as shown below. Okay, so the students move the trolley to the left. And then says the extension of spring A is 0.3 meters and the extension of spring B is 0.5 meters. The student releases the trolley. Calculate the initial values of the acceleration of the trolley. Okay, to calculate acceleration, you'll need the equation F equals ma, and I always put net. That's very important because this equation is for a net force. Okay, you can't just put any force acting on an object to work out its acceleration. It must be the overall net force you plug in here, and that's really important. So if we want to work out the acceleration, that's going to be the net force over the mass. So we do have the mass already, it's given it to us, it's 0.8 kilograms. We now need to work out the net force. Okay, how are we going to do that? Well, there's going to be, if the trolley's been moved to the left, okay, there's going to be a force trying to, when it's released, it's obviously going to go to the right when it's released. Okay, but there is going to be a force from spring A going to the left and one on spring B going to the right, and we've got to work out the net force. Okay, so we'll need the equation, okay, F equals kx minus kx, but we know the direction, so we don't need the minus sign. So if we work out the restoring force for spring A, that's going to be F equals kx. So that's going to be F equals k, which is 14, it gave us that previously, times x. What's that for spring A? It's 0.3. Okay, therefore F equals 14 times 0.3, which is 4.2 newtons. Now we need to work out the restoring force from spring B. Again, that's going to be F equals Kx, which is going to be equal to 14 because they're identical springs, times X for spring B, that's 0.5. So F equals 7 newtons. Okay, so just to go back to show you what we've done, we've worked out the force from spring B on the trolley, which is this one, which is 7 newtons. And we've also worked out the force from spring A on the trolley, which is 4.2 newtons. Does it make sense this one's bigger from spring B? Well, yes, because remember they're stretched initially in this position. They're each stretched equally. If it's moved to the left, okay, the extension from spring A is going to be less. Therefore, its restoring force is going to be less, because we said the bigger the extension, the bigger the restoring force. But when you move it to the left, spring B, the extension gets bigger, so therefore the force is going to get bigger. So it does make sense that spring B should have a bigger force if the trolley's moved to the left. Okay, what's the net force going to be? Because that's what we need. F net, the net force is going to be 7 minus 4.2. Okay, which is going to be 2.8 newtons, and that's going to be to the right because that's the bigger force. Okay, so we can now go back to our equation. Acceleration net force we've got now, it's 2.8 newtons divided by the mass, which is 0.08. Okay, oh sorry, not 0.08, 0.8 kilograms. And then if you plug that into your calculator, you'll get an acceleration of 3.5 meters per second squared. Okay, so the key thing here, F equals ma, but F equals ma, or I always write the net because it must be the net force that goes into here. You can't just put any force that acts on an object. It must be the overall net force that goes into here. Okay. So let's see part 2. It says calculate the ratio of the elastic potential energy for spring B to the elastic potential energy for spring A. Well, if you remember, elastic potential energy is half kx squared. So if I now use that and set up this ratio, we've got half, which is 0.4 times k times x. But this is for spring B, so I'm going to put B down there, squared, over 0.5 times k times x a squared. Okay, the 0.5's cancel, the k's cancel because they're identical springs. Therefore, we're left with the extension of b squared over the extension of spring A squared. So the extension of spring B, it says 0.5. So we've got 0.5 over 0.3 all squared. Okay, you plug that into a calculator, you get 2.8. There's no units because it's a ratio. Ratios don't have units. So we need to put that 0.8. So we can leave that as 2.8. Okay, moving on to the last few points. So explain why the acceleration of the trolley decreases as it travels a small distance to the right. We kind of touched upon that before. Okay, so it's saying why does the trolley decelerate as it's moved a small distance to the right? Well, if it's released from this point here, okay, if it moves a small distance to the right, what's going to happen to spring B? Well, the extension is going to get smaller because it's going to move to the right. We know it's going to move to the right because the net force is to the right. But as it moves, starts to move to the right, the extension on spring B will get smaller. Therefore, the restoring force will get smaller. But spring A, as it moves a slight distance to the right, the extension will increase on spring A. Therefore, the restoring force from spring A will get bigger. Okay, so the reason why it decelerates is because the net force, okay, is going to be smaller. Okay, and the reason the net force is going to be smaller is because the restoring force from spring B is going to become smaller, and the restoring force from spring A is going to become bigger. So overall, the net force is smaller. Okay, so you could put the resultant force, okay, is smaller. Okay, so last part says state and explain how the acceleration in your answer to II part 1 would be different when a heavy object is fixed to the trolley. So let's just go back and remind ourselves what is in part 1. Okay, so the acceleration of the trolley. So the equation is the net force over the mass, and it's asking what would happen if there was a bigger mass. Okay, well I hope you can appreciate that if there's a bigger mass with the same net force, because it doesn't tell us the net force is changing. So a bigger mass with the same net force is going to give us a smaller acceleration, or rather the acceleration decreases. So the acceleration, because it says state and explain how the acceleration will be different, the acceleration will decrease. Okay, that's the state part, so that will give us a mark. How do we explain that? We can just use the equation. You can say that acceleration is equal to the net force over the mass. Okay, then you can say since F net, or the net force, is the same, you could say a larger mass will result in a smaller acceleration. Okay, because this is implied in this question that the net force is going to stay the same. Well, if the net force is staying the same, a bigger mass will give a smaller acceleration. You can see that by that equation, just by stating that equation. If this value stays the same and you increase the denominator, then this whole fraction gets smaller, so A will get smaller. Okay, so that'll get you the second mark for the explanation. Okay, I'll stop that video for there.